chapter number 9, so flow through 5. Next things, all the details will be discussed here. So functional flow, losses in flow, connection in pipe, grade line, flow through pipes influence, and there is a branches of pipe network, hydraulic power, pumping power, miscellaneous problem. Okay, water hammer. Losses in flow, there is a two type of loss: friction, and it is made fluid friction, wall shear stress. This is the two type of major losses. That is, you forgot the shear stress. Shear stress is the main also, and there is a geometric changes. There is a major losses is the H major is FL v square by 2GD. The simple formula that is really helpful every cases, that is 1 by 12.1 FL q square by d over 5. So instead of remembering FL v square by 2GD, you can remember the 1 by 12.1 FL q square by 12. That is also called as Darcy-Weisbach equation. F is the Darcy friction factor, and there is a F is for F dash, where for F dash is termed as fanning friction, and F value you know, that is for tau 0 by half rho v square, half rho u infinity square by half rho v square. Now laminar flow, that is 64 by Re, and H is, you know, major losses increase linearly across the pipe. So major losses increased linearly across the pipe, okay, because L is in the numerator, okay, and the pressure is also decreasing. Got it? Now influence factor, that is H is f square by d over 5. Also you can write is 32 mu vl by lambda, that is the weight density, times d square. Also we can also like 128 mu ql by pi into lambda into d to the power 4. Question, there is a 2D and 3D. So for velocity constant, there is h is, the height is, velocity is, the head loss is proportional to 1 by d raised to the power 2, and for discharge constant, that is 1 by d raised to the power 4. So there is a difference. We cannot tell working without the d. So discharge, that is h equal to 1 by d to the power 4, h2 by h1 equal to 1 by d to the power 4. And in velocity is constant, there is the small points that are really important and makes a difference. When Reynolds number is smooth pipe, the velocity is Re is less than 10 to the power 5, and fanning factor is generally A into Re to the power 6. So Basselo's equation is really important. F dash is 0.31 x by Re to the power 0.2 to the power 5. So H equal to A by B. These are not important. So discharge position H is 1 by 5 minus B. So now given fraction. So now hydraulic diameter, that is 4A by B. So for rectangular, that is 2LB, because 2 is related to braid by L plus B. And for D, then it is 4 into pi by 4 d square by pi d, that is d itself also. And also number we can also write, that is rho v L by mu, or rho v L dh by mu, also v dh by nu. Nu is the kinematic viscosity. Minor losses, they are only 5 to 10% here that has happened, and they are not very much minor, so they are not really concerning for us. So losses due to abrupt changes, sudden expansion bending, and also for firing. So physical behind the minor losses. So there's a two type of things. When the area is decreasing, velocity is increasing, pressure is also decreasing. In this condition, higher total head to lower total head, what we are happening is that K is boundary streamline, they are just remaining constant, H equal to P plus K. So minus dP by dx is minus B. So pressure is decreasing along the length of the flow. Pressure is decreasing from boundary streamline. Total head from the pressure head should take place higher pressure to lower pressure. So total head from pressure flow should take place from higher pressure to lower pressure. That is happening. So there is no problem. But in this case, where the area is increasing, velocity is decreasing, pressure is increasing, so dP by dx, pressure gradient is positive. In this case, loss will take place where pressure gradient is positive. There will be AD boundary formation that will happening. So minor losses derivations. So first there is a increase. So there will be AD formation dP by dx, where increasing area dP by dx will plus VE, and that is will happen. So there is a control volume, that will everything will be H equal to V1 minus V2 square by 2 for sudden expansion. Now for sudden expansion, minor losses formulas is V1 minus V2 square by 2g, that you have seen when AD is there, velocity before AD and velocity after AD by deriving this. And there is exit loss, that is V square by 2g, there is V square. When some pipe that is a flow is increasing, that is H square by 2g. There is a sudden contraction that can also happen. So there is also AD formation, that is Vc minus V2 by 2g, that is Vc, that is V2. So Vc by V2, এখান থেকে V square we are taking common, so V2 by V2g 1 by Cc. Cc is the area of the sudden contraction. Now entry losses, that is k into v square by 2g, and h equal to height equal to 0.5 v square by 2g. Where it will use I will not know, but then I will see. So now there is a connection, that is the parallel connection, and there is a two type of connection: minor losses neglecting and mention considered. So single pipe which are reduced system pipe such that it creates some discharge and head loss called equivalent pipe. So here what will happen, A into V na, so it will compensate, the flow will remain same. So where the flow, the area's passage is decreasing, the flow speed will increase, or where the passage is increasing, the flow is decreasing. That's how it's maintaining. So Q1, Q2, Q3. So energy balance delta P1, delta P2, but delta P. So delta P is the head loss are just adding up. Head loss heading up. So delta HI summation 1 to n. So we can also write 1 by 12.1 FL Q square by dt over 5, and where L by D, that is the only change that is happening, Q is constant. So FL by dt power 5, we can summation F dot L by dt over 5. Also F is, we are just taking common, L by dt over 5, that is the main, that I equal to 1 to n L by dt over 5, the main equation, that is also termed as Dipitz equation. So this is a Dipitz equation. Then the second thing that is coming is that the parallel connection case, where there is a discharge that is increasing and there is a discharges are not same, they are just changing. So it is adding up, that is Q1, Q2, Q3, they are just adding up. And energy balance delta P1 equal to delta P2, so the head losses are same. Now energy lines, the gradient total line, because total is throughout the flow. Hydraulic gradient line, the losses of piezometric head rate and the piezometric head rate, semiconductor piezometric head rates and head is known as the losses because of piezometric head, known as the hydraulic gradient line. And energy flow line, total energy, that is P by rho g v square by 2g plus z, that is the energy gradient, and P by rho plus z, that is the piezometric head, that is called as head. So how is happening, you can see difference in energy is v square by 2g is difference, and expect reservoir always below, it is always below, and AGL can be moved up or down. AGL move can also move and down head loss of the turbine, and AGL moves up and down in the pipe involved. In case of uniform diameter, v square by 2g is constant, that is constant line. AGL, EGL will be parallel, they are parallel. Drawing energy gradient line, so you can see FLQ square. These things you just stop and have a look and just try to understand where what is changing in which case. So it is 0.5 v square by 2g. You can see there is a thing 0.5 v square by 2g, from where it is coming. You are seeing that there is a 0.5 d square h equal to, that is coming because there is a distance, that is the case 2, that is happening. There is a diameter is a constant. So this is how the things are happening. There is a constant change, those constant changes are there. So all these things you will need to see once again. So pump case, what will happen, the EGL and TGL will increase, and this case turbine, they are just dropping. So the dimples of the valves are intentionally provided because the layer, it has more momentum. The layer, since it has more momentum than the laminar boundary layer, can resist adverse pressure gradient. Okay, now flow through siphon, that is important, flow through siphon. So this is the line above this, it is a P1 by Vg plus Og. So here it's a vacuum, and flow of AGL pipe implies that gauge pressure, that is V into A. So flow above the AGL is 0, flow above the AGL is 0, flow in intersection is minus, flow is the intersection is minus, flow above the AGL line is 0. It is also limited to siphon, not but everything. So you need to see all these things. Now branching of pipes, how, from where it is coming, how it's meeting and how it's going, and where this type of flows are there, you need to do the maths. Now hydraulic math, so the efficiency is netted by gross it, 1 minus h by h, power equal to lambda qg or rho qgh, actual power. So you can know A equal to 66.7%. Now nozzle actual maximum, so everything is deleting, this is a nozzle equation, h equal to v square by 2g plus head losses. So FL v square of everything, so D equal to 4 into d over 5 by 4 FL for actual maximum power. Variable losses, there is a variable area that we can see, h equal to 1 by 12.1 FL cube square by 4 into d1 minus d2, 1 by d2 square minus d1 square to the power 4, and h equal to 1 by 12.9 FL cube square by dv to the power s. dv, you can see where is dv and dv and ds, how is coming. And variable discharge cases we are coming. So variable discharge, h equal to 1 by 3 for constant variable discharge. Now water hammer, how is happening when the valve is closed, sudden drop in kinetic energy enters in the compressor pressure wave and propagates in the direction against the flow. It is propagating against the direction against the flow. The striking of the wall by the known as the water hammer. So sinkage tank. So there is a surge tank that has been installed to compensate the install. So rise in pressure, it is V rho L by geometry value. This is critical time of the closure, that is the time taken to the pressure wave to propagate, that is L plus L by C. C equal to K by rho, you know C equal to K by rho, that is the elasticity. Actual time TA is the time taken for closing. So actual time is greater than TL, that is gradual. Actual time less than the TC, critical time, that is the sudden observation. So gradual closure, that is a gradual closure is a rho L V by TA, and P equal to F by A, you know. So rho A L V by T into A for a gradual pipe, and for sudden pipe how is happening, and this is the end.